Thank you for the very kind words there. And yeah, just thank you for inviting me. Yeah, really excited to talk about this. And I think, as I was kind of saying just before we got started, I definitely want to go and present our results today using AIs to go and code open text questions from surveys. But I also want to give a bit of a flavor as well of just a general guide of how you go about using these tools, because they are still very new in their current form for all sorts of research tasks, and give you an idea of some of the considerations, but also where things could potentially go wrong, ways in which you can fool yourself into thinking these are more capable than they really are. So that's definitely want to give a kind of overview there. So if you want to find out more about the paper, I've put the link up here. But actually, I think maybe the most interesting thing, if you want to apply it yourself, is we also have the replication code and the data. And that includes all of the prompts, all of the API calls, all of the surrounding codes to actually go and use this yourself. So we've tried to make that as accessible as possible for people to actually go and use this for their own projects. So I'm mostly today going to talk about this paper recently published in Research and Politics about using AIs to code open text questions. But I will draw on a couple of examples as well from other projects where I'm using LLMs. One of these is one building on that instrumental variable paper Rohan mentioned at the start, where I'm going and scraping causal claims from as much academic literature as possible using these large language models. And yeah, it's been very interesting to see what they can get. It's incredibly impressive at times, and also the places where they fail as well. And the other use of LLMs I've been doing a lot lately is supervising a capstone group of students to build AI bots to go and help with education in the classroom. So in this case, they built a Portuguese conversation bot that on the right-hand side would have a conversation with the students in Portuguese, and on the left-hand side would give them personalized feedback on how their response was, give them grammatical corrections, better ways of more naturally conversing. And I've used similar things to this in my own teaching with teaching qualitative research methods, so having the bot act as an interview subject. So I think there's a lot of interesting things there. I'm going to use a couple of examples from that in talking about how to go and construct these prompts as well. So just to give an overview of what an LLM is, I think probably most of you are at least somewhat familiar with it by now. Large language models are fundamentally text completion models. So they have a dependent variable of what is the next word going to be in this chunk of text. And the independent variables are various functions of the text that has come before it. Now, it turns out that predicting what the next word is going to be seems to be easier with these models, which are generally neural networks, if they include some level of abstraction. Now, there's a whole philosophical and technical debate over whether this counts as understanding, but I will say, at least for the frontier models, a useful mental model is to kind of treat them as if they are understanding in practice. So although we can have the philosophical debate about what truly is intelligence or anything, you get better performance out of these things if you treat them as if they were something that was trying to understand what you're saying. And the models are further trained on human feedback about what is a useful completion. So they end up predicting not just what is the most likely next word, but what is the most likely next word in a useful response that would help the user who is requesting it. In practice, this creates a model that can complete a variety of useful tasks without explicitly being trained on them. So, this can also be tasks that will be useful for social science research. So here's just a very quick one. This was a tweet from Nigel Farage, and I just asked it to go and take the sentiment towards different countries from this. And you can see there that ChatGPT is able to give back. It mentions the USA neutrally and mentions Europe negatively. And I think that is a correct reading of that text there. Similarly, you could go and do something like telling the LLM to go and extract mentions of public spending and whether it increased or decreased from a news article. And you can see there it's done a reasonably good job here, saying that the IRS is its budget's being discussed, and then in the next one it talks about the budget reduction within it. So these are examples of where, at least anecdotally, you can get some performance on tasks that you might usually get an RA to do. The one I'm going to talk about mostly today is open text survey responses. So the standard way of doing surveys is you ask a question with a close-ended set of responses. So what party are you going to vote for, and then give a list of 5 to 7 parties. Here's a statement. How strongly do you agree or disagree with that statement? And that's good because it's very easy to analyze, but it has the negative effect because you prime respondents to give particular answers, and you can only ask about things you think about in advance. The advantage of open text survey responses is people can come up with things that you didn't even think of. They can say what is meaningful to them. But the big downside is open text data by itself is useless for empirical analysis. So instead, you usually have to go and code those responses into some kind of closed-ended categories. And that, again, is expensive, time-consuming, and therefore people tend to limit their use of these questions. So if LLMs can code open text well enough to use in public opinion research, maybe we can make greater use of this tool, more effectively go and conduct this kind of research. I'm going to take this from the British election study, which I helped run. So the British election study goes all the way back to 1964. We've been running it since 2014. And there's been 25 waves with around 30,000 respondents per wave in the internet panel. And in each of these, we have asked, what is the single most important issue facing the country at the present time, with people able to give any open-ended response they like to that. So the approach so far has, so this is used as an indicator of issue salience, what issues are important to people, and therefore what might drive their vote choice. And so far, we have RAs go and assign 50 granular categories and then 13 collapsed categories to these open responses. And we've manually labeled over 500,000 open text responses to this since 2014. So this is, a large amount of work that humans have had to do manually. Obviously, it would be good if we could do this faster and cheaper and potentially do a lot more of these if we didn't have to go and get RAs to do it every time. So these are the categories. I'm not going to go through all of them, but it just kind of shows the way and the types of answers people can give and what we code them into. So we have various economy categories over here. We have health. We include coronavirus in that, immigration, Europe, some kind of liberal authoritarian, so sort of cultural liberalism versus cultural conservatism categories, and same with left-right, some things that tend to be kind of, economically left or right focused. So these are some examples of what this data looks like. You'd end up with people saying, strikes, that gets coded into economy, an incompetent government spelt in every possible way. That will get coded into political negativity. An out of control cost of living crisis becomes living costs. So you can see that you go from this very messy open text data into this, relatively neat set of 50 or 13 categories. So what counts as a good performance on this? It can be just tempting to go and grade, okay, well, we have this human-coded data. How close does the AI get to replicating the human data? And that is a useful benchmark, but it is important to recognize that even humans don't get 100% right. So if the AI ends up agreeing with the human 80% of the time, or 90%, or 95%, is that a good or a bad performance? Because if we get a second human to code it, they will not necessarily go and code it identically to the first human either. So we're going to use two relevant benchmarks. We're going to use a second human who independently coded our data. And we're also going to use state-of-the-art supervised models. I can talk more about these in the Q&A if you're interested. But essentially, they are text-specific ways of going from labeled training data, where you have the text and the labels, and then making inferences about unlabeled data on the basis of that. So one of them is DistilRoBERTa, the other one is a neural network fitted to BERT embeddings. And these are kind of a halfway house between traditional statistics or machine learning and full-on large language models. So this is a very relevant benchmark. This is about as good as you can do with a supervised approach. So how do you go about accessing an LLM? So the way most of you will probably have experienced this so far, unless you've already started doing research, will be through a web interface. So you go on to ChatGPT, you go and say something, it gives you something back. This is good for kind of small-scale research tasks, such as, hey, tell me where the bug is in this piece of code, go and fix the grammar in this paragraph. But this really doesn't scale. This isn't a good way of coding 500,000 survey responses or extracting information from 5,000 articles. That's not really designed for that. There's still a very manual process, a lot of copying and pasting. So instead, there are two options that researchers should probably be using for research at scale. Either host one of these models locally, which will have to be an open access model, or you can go and call these models through an API call. And this is an example of some R code here that is doing that API call, where you go and systematically send your request to OpenAI or one of the other providers' servers, and it gives you the LLM response back. So you can deal with that programmatically, and therefore go and deal with it, in part of an automated workflow. So what do these API calls look like? So this is an example here of OpenAI's. This shows their playground, which has all the same features as their API, but in a user interface. And then you can very easily convert this into an API call. So you'll generally have a system prompt that is the instructions of how you want the bot to act in response to what you're doing. So this is all the coding rules here in how to go and deal with these survey questions. You also want user input. So this is the data here of the survey responses we want coded. You then have various options, such as what model you want it to use, GPT-4 in this case, and various other parameters as well. The most important one here is temperature. This is how much randomness the AI will use when it generates responses. So if you set this to 0, it will always pick the most likely next word to complete the text, and you'll get the same result every time. If you go and set it any higher than that, it will be somewhat stochastic. You won't get the same response every time, but they will be arguably a little bit more creative. And you just need to be careful that you pick a maximum length that goes and fits in the entire response you expect. Then the assistant response down here, this is an example of the output it would give. So you can see here it's gone and given us the original survey response plus the category that's relevant. All of those categories look pretty good here. But obviously, we're not going to go and do this manually through the web interface. Instead, we'll convert this into API call code. So this is just showing here how the parts of this interface correspond to parts of the code. And you can see here, it's really not that much code to go and start working with this. This is R code through HTTR package. And yeah, you can get up and running with this very quickly. It's not complicated to get going with these models. So how do you go and write a prompt that will get effective performance for your research tasks? Now, there's a lot of kind of folk wisdom out there about, one weird trick to get good performance out of the model. People claim you can offer it a tip. You can threaten it. You can say you're going to shoot a puppy if it doesn't go and give you well-formatted JSON. These are not really real. They might have worked one time on one model. People kind of repeat them because they're fun more than that they're effective. Instead, I'd say the key things you should focus on are providing context to the model so it knows what you're trying to do and what the context is of the task, specifying the intended behavior in a lot of detail, addressing edge cases. So if there is a hard call, trying to give it guidance on where to go on that call, and then iterating through trying out a prompt, seeing where it goes wrong on a small test sample, and then fixing the prompts to try and address those errors so you get closer to the desired performance over time. So if the model fails on the first thing you try or doesn't do well, that does not necessarily mean it won't be able to do that task or do it well. It may mean that you need to go and specify the task better. And it's worth going through a few iterations before you give up and say, it just can't do this. Often better prompting can get you there. If you want it to go and follow a particular train of logic, you're also going to want to spell that out as much as possible. Okay, so let's go and show an example of this. So this is the prompt we use to go and get the survey responses coded. So we start with some context. Here are some open-ended responses from the BES to the most important issue question. We then tell it what the output format we're looking for is. Please assign one of the following categories, returning original response and most relevant label. And we give it a bit more instructions about only use the labels provided and not to go and miss any responses. And then we start explaining what we mean by each of the categories. We list the categories, give a little bit of information in addition to the category name about what we're looking for there. So we also give some extra context. So these models were trained in some cases before the invasion of Ukraine. And so we had to go and provide that context of, by the way, if people keep mentioning Russia, it's probably because of the war there. And so that was important information to provide because that would not be within the training data. So it has no way to know this. And we also gave further information about the output format, gave a couple of examples of what we wanted and cases where we wanted it not to respond in certain ways. One additional thing that these models will tend to do is they want to go and be conversational because that's what they've been trained on. They want to go and say, I hope this is helpful. Here is the JSON you requested in this great format. I hope this works for you. And that is terrible if you want to go and read it in as code because that random natural language can completely mess up your parsing structure. So as much as possible, you want to go and tell it not to do that and to go and follow a very strict format. You won't get 100% on this, but this can improve it a lot. So we also went through this iteratively. So a lot of these categories, we gave more information when we saw places where it got it wrong in our kind of small testing on, maybe 50 total examples, and gave more information about, okay, political correctness, we kind of want you to put it into this category, wokeness type responses, that's relevant here as well. Because the model may potentially have said wokeness is a liberal response, but we kind of know, oh no, this is an authoritarian thing someone is saying. So we were giving it that context to go and better answer. And you will find that giving this kind of information significantly steers how the model will respond. So giving that extra detail can improve performance a lot. Similarly here with domestic emergency, we're telling it, okay, these things are examples of that, but don't include COVID because we have a separate category there. So again, we're addressing edge cases, explaining where the boundaries of our categories are. And this, again, should feel fairly familiar to instructing a research assistant to effectively go and complete a task. You're just going and giving them all that context. The key difference is with a research assistant, often that will come through a back and forth conversation about what about this case? I'm not sure here. You'll give them a response. With the LLM, you don't have the opportunity to do that. So all of that context, all of that back and forth conversation has to be encoded within the prompt itself. So you have to give a more detailed description of the task initially than you might have to do for an RA, because the RA can come and ask you questions, and this isn't set up to do that. So this is an example of what the Portuguese chatbot looks like. I'm not going to go through all of this, but just to show another example of where following these same rules leads to pretty good performance. Giving context about who they're talking to, what it's meant to be, telling it to limit its response to 10 words or less. By default, these models and conversations will just spew 3 or 4 paragraphs at a time. For a kind of language learning bot, that's not effective. You have to go and tell it if you want a shorter response than that. And you're also telling it then about intended behavior, what it should do, what type of language it should use, what it shouldn't use, and also what topics you want it to talk about, which are hitting on the lesson objectives for this course. Finally, from the causal claim extraction project, this was the one where extracting causal claims from academic papers. This one, we were very, very specific about wanting a JSON formatted output here and what we wanted in it. And we're telling it, even within each of those fields, how to go and deal with if it is uncertain about an answer, how to go and give that information, giving true, false values, saying link not found as opposed to some other text. Because again, you have to make this as possible by a computer on the other end as possible. You don't want it to have given you, I couldn't find it in 30 different ways. You don't want to have to go and code that all manually. You want to specify how this thing should respond each time. And here as well, with the number of countries covered, there was quite a complicated set of rules we had of how to go and include or not include countries. And so here we had to go and specify that in quite a lot of detail, what steps of logic to go through for whether you count a country as included or not. And out of the other side of this is the first prompt in a whole series in this paper. It was able to correctly give this information in a format that could be parsed by a computer. So it was able to give the DOI, specify whether this was a statistical paper, give a subfield, and say what countries were included and whether that was a complete set of countries or not. Okay, so hopefully you will end up at this point with some LLM outputs, or at least somewhat computer readable, but in practice, they're not going to be 100% there. And so you will improve your performance a lot if you look at the places where the format is slightly off, and you're going to have to write code to go and deal with that. So for the MII project, we stripped out common formatting errors, extra white space. They often like to use bullet points. We put everything into lowercase because the LLMs insist on correcting the capitalization of our categories. And we also resubmitted survey responses that the LLM didn't code accidentally on the first time round up to 2 times. And all of these together, at least for some of the lower performing LLMs, quite dramatically improved the performance. So by having this surrounding code that better implements the LLM, you get much higher performance than just using the prompt and taking it exactly as it is and saying it failed if you can't read it into the computer perfectly the first time. Higher performing models are going to need less of this, but even the best model out there, GPT-4, does make some errors like this. So it is worth going and writing some of this surrounding parsing code that can go and deal with obvious errors, and you will get the success rate up substantially by doing that. So we tested over 20 large language models for whether they could complete this task at all. And this isn't completing it well. This is just giving us back something that we could use at all. And essentially what we found was OpenAI's models could complete this task generally. Anthropic's models, Claude, could generally complete this task. And Google's latest models were just about able to as well. The only open source model that we were able to use even complete this task at all was Meta's Llama 2. Every other open source model was unable to complete the task, and a number of closed source ones were not able to either. And when I say not able to complete the task, this was one of the examples here. When we gave it a list of survey responses, it just said the issue facing the country is health, including the NHS, which is not responsive to the task we were trying to get it to do. Another example was this one, which just repeated health include NHS over and over and over again, which again is not really going and answering what we wanted it to. And finally, one that just repeated Brexit, 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 Brexit over and over again until we stopped it responding. So it really is a recent development in large language models. It's only the very latest ones that are able to complete tasks like this effectively at all, where you can even give them a score on it.
John, just briefly, are you able to just go back to, there's a brief clarification question. Was Mistral tested at all?
I think Mistral was not tested at the time and was not available at the time we ran this. So yeah, when we were running it, I believe Llama 2 was the most performant open model. Yeah, another thing I should say with this is not a claim about open source models for all time. This is a claim about a snapshot at the moment we ran this, what was capable of doing it, what isn't. I fully expect that the open models are going to reach at least the performance that closed models have now, and may well catch up to them. So this is even now, this paper was just released a couple of weeks ago. Even now, this is a snapshot of the world as it existed several months ago when we ran this. So as Rohan has absolutely correctly said, there are new models that have been released since then, and we probably will go and benchmark those and slightly update this to see whether or not ones such as Mistral can go and reach that performance, which will be interesting to see.
Thank you.
So how are we going to assess the accuracy? We're just going to use a very, very simple statistic here, which is % agreement with the original human coder. In the appendix, we do have a ton of other indicators of success, but they all show exactly the same pattern. So we're just really going to focus on % agreement here. But just be aware that, the other indicators are going to show the same things. So, if you're worried that this is one metric and other things might show different, they all show the same patterns. And we're going to be testing 6 LLMs, ones that were able to complete the task. So 2 from OpenAI, 2 from Anthropic, Tom 2 from Google, I should say, and Llama 2 from Meta. Also have 3 supervised models in there, the 2 kind of state-of-the-art ones, plus old-fashioned SVM, which is the kind of standard thing you would get out of the box if you go and do this kind of machine learning in R. And also a second human who is a co-author on the paper who had never been involved in this task before, in order to see, okay, compared to getting another person to do this, how does the machine perform? So we're going to look at 2 scenarios here. The first of these is, imagine that you're asking an open-ended question for the first time. So there is no existing training data on this. You just wrote the question, last week, you fielded the survey, now you have 5,000, 10,000 survey responses back. So typically, what you would do with that is you would go and sample a relatively small section of those and have an RA train them, and then fit a supervised model to go and fit labels to the rest of the sample. So, rather than having to code all 15,000 responses, maybe you just code 1,000 and use a model to go and label the rest. The LLMs and the humans on this are going to code based only on the instructions. They get no specific training data for this. And the performance is going to be scored on 81,000 cases from waves 21 to 23 of the BES Internet panel. The second scenario we're looking at is one that, the scenario we're actually in, which is an existing question that's been asked a lot before. This represents where there's a long-standing question, tons of available training data that's been asked for a long time, but we've just done a new round of data collection and we want to label that new round. And the key thing here is that when we're labeling a new round of data collection, we actually only care about new text responses, because for duplicates, things that have been answered exactly the same way before, we can just copy those labels over. You don't need a model for that. You could just, write one line of R code that will just match the labels. So we're going to be testing the performance on totally new text responses in this scenario. The supervised models, though, are going to get nearly 600,000 labeled cases to train on from waves 1 to 20 of the BFIP. And then the performance is going to be scored on the 14,000 new text responses from waves 21 to 23 of BSIP. So this is, kind of the other major scenario of how you might use these. And let's see how they perform. So this is the new question scenario where you've got that totally new question. For the supervised models, you train, say, on basically 1,000 cases. And what we find here is that the large language models, the best ones, which are Claude from Anthropic and GPT-4 from OpenAI, they essentially equal human performance. They actually beat the humans slightly in a couple of cases. I don't think that's significant or meaningful. It really depends on the metric. But they are essentially meeting human performance here. They are agreeing with the original human about as often as the second human agreed with the original. So that's true for the frontier models, so the latest Claude models, the latest GPT models. But your performance falls off a lot for even Google's PaLM model, and especially for Llama 2, the performance is far, far lower here, really to an unacceptable level. So the solid line here is the 13 category agreement, and the dashed line is going to be the 50 category. So obviously that's going to be structurally lower because you can be slightly wrong, but still within the same larger category. And I'd say the 13 category agreement is probably the most relevant one from the perspective of what you would use in analysis, because you're unlikely to want to use 50 dummy variables in your regression model. The 13 categories is kind of what people will typically end up using. What about the supervised models? So the best supervised models, which was the neural network fitted to BERT embeddings, perform reasonably close to human level, but still below the best LLMs. So, the state-of-the-art supervised model trains on a sample of the actual data it's trying to code, underperforms a zero-shot LLM here that's just accessed through the API with no custom training data. So that's kind of where we are in the benchmark of you're using this for a new question. What about the existing question scenario? So remember, this is a scenario where you've got all of that old training data, but you just want to label the new cases that you haven't seen before. And so on this one, humans still do have something of an edge, especially on the 50 category coding. There's around an 8 percentage point improvement of human over frontier AI model performance. However, it is notable here that the large language models with zero shots, so no examples shown to them, are outperforming by a significant degree the best supervised models trained on over 500,000 older cases. So, well, the large language models are not, at least on the 50 category metric, quite meeting human level, although they're not miles below it. There is a meaningful gap, though. They are beating supervised models trained on a dramatically larger data set that's specifically tailored to this problem. On the 13 category one, again, all performance tends to be quite a bit higher. The large language models, the best ones, are within a reasonable distance of the humans. So if you were using the 13 category version of this, you're probably getting acceptable performance with a large language model. And that is going to then still outperform the supervised models trained on over 500,000 cases. So if you're using the 13 categories, large language model is probably acceptable even in this existing question case. If you really care about the 50 categories here, where you're breaking it down that granularly, then human performance is probably what you're going to need. You're probably going to need another human to code it rather than a machine. But for the more aggregated one, the large language models are nearing human level performance. So where did the large language models go wrong? So I'm going to show some of the errors that are from a slightly earlier version of the paper, where GPT 3.5 said war was the category, and the original human coder said foreign affairs. And I just show this to illustrate that often the errors that the large language models make are quite human. So you can see here that these kind of are both, they're really an edge case between foreign affairs and war. So they may not explicitly mention the word war, but they are very much about the Ukraine war. And to be honest, after we finished this paper, we ended up going back and going with the GPT choice here, because we felt that actually these probably were better understood as war responses than foreign affairs responses. So even where the LLM is making errors in terms of not agreeing with the human, we're not always 100% convinced by the human choice above the LLM one. This was another case here. I think we did stick with our original coding, but it was very understandable why the LLM made the error. The LLM said COVID economy, so the kind of economic effects of COVID. The original human coder said coronavirus. And the economy is not explicitly mentioned in these, but is very much implied. Recovery from COVID. Now, that could be a purely, recovering in the sense of fixing the virus, not going into having people infected anymore. But it's also quite understandable that the LLM inferred that economic recovery was meant by that. So again, a place where the AI fails to agree with the human, but in a pretty understandable, nuanced, it's kind of, you could go either way on this kind of way. And this tends to be the pattern of the errors we see mostly. There aren't a lot of errors where you just say, well, the LLM just didn't understand what was going on here and the human nailed it. How much does all of this cost? So this is, of course, the other big thing here. Across all testing, we went through about 3 rounds of this. We spent around $100 with OpenAI, mostly on GPT-4 calls. Since then, GPT-4 Turbo has been released. That's about 1/3 of the cost of GPT-4. And then GPT 3.5 Turbo is about the 20th of the cost of GPT-4 Turbo. So you can get a 60-fold reduction in cost if you use GPT 3.5 as opposed to GPT-4. Although the performance, as you'll see from the previous charts, is lower with GPT 3.5. But the key trick here is you should sign up for Anthropic's Claude if you are able to. I'm not sure if it's available in Canada yet, unfortunately, because they give 2 million tokens of free requests per day, which was enough to code all of our survey responses. And I strongly recommend taking them up on this offer because they are funded by Amazon, funded by a bunch of venture capitalists, and you should just spend their money while you have the chance, because this offer won't last forever. It's very easy to then switch away to another one once they eventually shut this down. But for now, they're giving away, $15 worth of free credits a day, essentially. And you might as well use that money because it's a very good deal. Google's Palm 2 is also free, but it's not very good, so I don't recommend that. Llama 2 we accessed through replicate.com, which is a site that hosts open source models. This was very expensive. It was about 10 times the cost of GPT-4. But you could run a copy for free if you do have the hardware, either on your own computer with a $1,500 GPU, or if you have access to a computing cluster, which may be able to do this for you. So if you happen to have the computing resources, Llama 2 is an option, although it did not perform well in our tests. But we do expect that future open models are going to perform much better. Speaking of that, open source LLMs obviously have the advantage you can run them locally, and that is free, at least at a marginal cost level. And they're fully reproducible, unlike closed source LLMs, which often change, and it's very non-transparent why they change. Or humans, for that matter, who can make different choices on different days. Humans do not do the same thing every time. The downsides, of course, are at the moment, at the snapshot of when we did this, the performance of open models was just a lot lower. And the hardware requirements are high and expensive. And compared to API calls, they are relatively complicated to use, although they are getting easier all the time. People are improving this. So just to summarize the results, the best LLMs are close to human-level performance in coding open text survey responses, and the best LLMs beat the state-of-the-art supervised methods on the relevant benchmarks. Which LLM you choose really matters. You probably, at the moment for this kind of task, would want to go with either OpenAI's best models or Anthropic's best models. But LLM's performance can be greatly improved with careful iterated prompt design and the cleaning of outputs. We found large performance improvements by appropriately designing the prompt and by dealing with the messiness of the outputs in a way that didn't go and code responses wrong just because they came in the wrong format. So that's a summary of the results today. I hope that was useful. I'm very happy to answer any questions about this, of how to use these generally, any of our results in more detail.
Thank you very much, John. Fascinating presentation. I'll stop